This is your presenter Asloob Mudassar, and I am presenting slide number 41 of the course on laser physics. Question is, calculate the absorption cross section under inhomogeneous broadening sigma in when an ensemble of anti-atoms per unit volume is considered. The answer is, the inhomogeneous broadening cross section sigma in is related to the inhomogeneous transition rate W in through the flux F of the incident beam as given. That is, sigma n is equal to inhomogeneous transition rate divided by the beam flux. That is, sigma in is equal to W in divided by F as given in equation number 41.1. The inhomogeneous transition rate W in can be computed from the total power absorbed per unit volume per total photon energy absorbed. If we denote the total power absorbed per unit volume by dP over dV, and the total photon energy absorbed is equal to Nt into h nu, where Nt is the number of atoms per unit volume and each atom has an energy h nu, then Nt into h nu will be the total photon energy in that region. Then W in is defined as W in is equal to dP over dV divided by photon energy Nt into h nu. So then that becomes the total power absorbed per unit volume divided by the total photon energy as given in equation number 41.2. So let me read again. W in is equal to dP over dV divided by Nt into h nu. We thus need to compute dP over dV if we want to find W in. In inhomogeneous case, the resonance frequency of an atom nu naught prime is distributed around some central frequency nu naught through a distribution function denoted by G star. G star of nu naught prime minus nu naught, where this star actually is the complex conjugate of G. So I shall be reading it as G star of nu naught prime minus nu naught. So you see that in the case of inhomogeneous case, the resonance frequency of an atom nu naught prime is distributed around some central frequency nu naught and is given by this distribution. The elemental number of atoms, which we denote as D and T, with resonance frequency between nu naught prime and nu naught prime plus D nu naught prime, is computed using the relationship that is D and T, that is the elemental number of atoms, is equal to Nt into G star of nu naught prime minus nu naught multiplied by D nu naught prime. So this will give you the elemental number of atoms which we have computed over here, and this is of course particularly associated with the inhomogeneous broadening. And the elemental power absorbed, which is D, you see that we have used D to stand for the elemental power absorbed. So D of dP over dV by this elemental number of atoms D and T is computed as given. So you see that now we are going to calculate the dP over dV for this D and T. So that's why we have also labeled it as elemental power absorbed. So D of dP over dV for the elemental atoms D and T is computed as given in equation number 41.3. So we have on the left hand side we have D into D of dP over dV is equal to D and T into h nu into WH of nu minus nu naught prime, and we have substituted the value of D and T from this relation given over here in the red, and we have substituted that value of D and T over here, and then we have h nu, and then we have WH of nu minus nu naught prime, where WH of nu minus nu naught prime is the homogeneous transition rate for those atoms having resonance frequency equal to nu naught prime. You know that when we talk about the homogeneous transition rate, it means that we are assuming that all the atoms will resonate at only a single frequency. That's why we have said over here that WH of nu minus nu naught is the homogeneous transition rate for those atoms having resonance frequency equal to nu naught prime. Now we are going to take the integral of both sides of equation 41.3. And you know that the integral will cancel out this small d just before dp over dv, and also it will cancel out the small element d just before nt, that is d and t will be replaced by nt, because on the right hand side actually we shall have the two integrals, one at d and t, the other integral at the rest of the quantities. So we have nt into h nu on the right hand side, and of course the integral of wh operating wh of nu minus nu naught prime into g star of nu naught prime minus nu naught, and the integral is with respect to d nu naught prime. That is, we are integrating at all possible frequencies that the atom could resonate. Thus the inhomogeneous transition rate is given by. So you see that in the previous formula we are now substituting the values of these quantities, that is dp over dv from the above relationship. We are going to replace that one over here. So Win is equal to dp over dv divided by the photon energy nt into h nu. So that becomes equal to integral of wh at nu minus nu naught prime into g star of nu naught prime minus nu naught, and the integrand element is d nu naught prime as given in equation number 41.4. The other quantities which we have not shown have been cancelled out, that is nt and h nu will be cancelled out with the terms in the denominator over here, that is nt and h nu will be cancelled out, and we have the rest of the quantities over here. So it means that we have found an expression for the inhomogeneous transition rate given in equation number 41.4. But from equation 40.1 in the previous slide, that is in question number 41.1, we have defined sigma h, that is the cross section for the homogeneous transition, is equal to wh divided by f. That is the transition, that is the transition rate in case of homogeneous broadening divided by the beam flux capital F. So this is what we have explained in the previous slide, that is sigma h is equal to wh over capital F. So you see that I have labeled in equation number 41.4 wh was represented in the red color, and I have also used wh in the red color over here. So it means that I shall be replacing wh in the integral by this relationship, that is wh in the integral will be replaced by f into sigma h. And you know that we have win can also be defined as f into sigma in. As we have wh defined for the homogeneous case, then for the inhomogeneous case we can define win is equal to f into sigma in. And you know that you can also follow this definition from over here, that is Win is equal to F into sigma in from equation 41.1. The same definition is what we have used over here. So Win is equal to F into sigma in. And you know that we have so Win, but Win is equal to this quantity, that is the integral. But in the integral, as said earlier, that in the integral wh will be replaced by f into sigma h. So I am substituting the value of win in this expression, which is equal to f into integral of sigma h nu minus nu naught prime into g star of nu naught prime minus nu naught, and the integrand is with respect to d nu naught prime. So this is win found over here. Thus, using equation 41.1, we can write, so from here we can write sigma in is equal to Win divided by capital F. So F will be cancelled out over here, and we can write out the inhomogeneous cross section sigma in is equal to the integral of sigma h, which is the homogeneous cross section, as a function of nu minus nu naught prime into g star of nu naught prime minus nu naught. And the integral is with respect to d nu naught prime. Sigma h nu minus nu naught prime within the integral differs for each atom due to different resonant frequencies nu naught prime, which is due to inhomogeneous broadening. You see that the homogeneous, when we define sigma h, it remains the same for all the atoms having the same resonant frequency, nu naught prime. But you know that in homogeneous case, this nu naught prime will vary from atom to atom. So different atoms can resonate at different values of d nu naught. That is why we have the integral with respect to d nu naught prime. So this nu naught prime will have different values in the inhomogeneous broadening case. So this sigma h will also vary. For one frequency nu naught, it is fixed, it is uniform. But since different atoms have the possibility to resonate at different value of nu naught prime, that's why we have the integral with respect to d nu naught prime. So that's why this will be different, this will differ for each atom due to different resonant frequency nu naught prime, which is due to inhomogeneous broadening. Thus sigma in may be considered as an effective average absorption cross section. The value of sigma h from equation number 40.2, that is from the previous slide, can be written as this is sigma h as a function of nu minus nu naught prime is equal to 2 pi square over 3 n epsilon naught ch into absolute square of mu into nu into g of nu minus nu naught prime. This is the expression that we have obtained in the previous slide, that is in slide number 40. And then we are using this value of sigma h in the above integral, that is in equation number 41.5. So we have the following result: sigma in is equal to 2 pi square over 3 n epsilon naught ch into absolute square of mu into nu into the integral from minus infinity to infinity containing two functions. One is g of nu minus nu naught prime, the other is g star of nu naught prime minus nu naught, and the integral is with respect to d nu naught prime. So this integral in blue is what we represent it with the function gt of nu minus nu naught, written just below, because you see that in the above integral the integration is over the variable d over the variable nu naught prime. So this nu naught prime will vanish out through the when the integration has been performed. So the new function that will appear is denoted by gt, and you saw that this gt does not contain nu naught prime. So gt is a function of nu minus nu naught. Where gt, so you see that we have also given the explicit form of the gt in equation number 7 as gt of nu minus nu naught is equal to the integral from minus infinity to plus infinity, the same integral that we have written over here. So g as a function of nu minus nu naught prime into g star of nu naught prime minus nu naught, and the integration is with respect to d nu naught prime. As both g and g star are normalized to unity, so is gt, that is the integral from minus infinity to plus infinity of gt as a function of nu minus nu naught with respect to d nu is equal to 1. We can rewrite equation number 41.7, that is this equation, for useful interpretation as, so equation 41.7 can be written as this. So the right hand side has been changed because we have introduced the variable x is equal to nu naught prime minus nu naught. So due to that one, the integral has been modified as shown. That is, the integral contains integrand as g star of x multiplied by g of nu minus nu naught minus x, and the integration is with respect to dx now. So you see that if you recognize this one, this integral, this is nothing but the convolution between the two functions g and g star. This is what we have also written, that gt is the convolution of g and g star. So here we can understand the meaning of gt. So what is gt? gt is nothing but the convolution of the two functions g and g star. Now let's discuss the two cases. For example, look at the integral. This integral contains in the integrand two functions g and g star. So let's accept the possibility that g star of nu naught minus nu naught prime minus nu naught is equal to delta of nu naught prime minus nu naught. That is, when all the atoms have the same resonance frequency equal to nu naught. due to the presence of the delta function. This is due to the presence of the delta function that we say that when all the atoms have the same resonance frequency equal to nu naught, because here the delta function will be non-zero only when the nu naught is equal to nu naught prime. Then from equation 41.7 we have, so you see that if you use this value of, that is you replace g star with delta function in this equation, then of course this equation will give you gt of nu minus nu naught is equal to g of nu minus nu naught, and the sigma in becomes equal to sigma h, because you know that in the definition of the sigma h we have only the function which is present is g of nu minus nu naught. So let me show this sigma over here. So this is, you see that sigma wh is present over here, and we have written the value of wh over here. This is, you see that wh contains sigma h contains g only, g function. So that's why we say that in case 1 we have when we set up g star is equal to delta, then of course we obtain gt of nu minus nu naught is equal to g of nu minus nu naught. So gt will be replaced by simply by the function g. So that's why we say that the sigma in this case becomes equal to sigma h. So the case 1 is thus the case of a pure homogeneous broadening. So now let's discuss the case number 2. Let's choose now, for example, in this you see that in the previous case we have, in the case 1 we have chosen g star is equal to g star is equal to delta. Now we are going to select g equal to delta function. So if you choose g as a function of nu minus nu naught prime is equal to delta of nu minus nu naught prime, that is when the width of the homogeneous line width is much smaller than the width of the inhomogeneous line shape, then from the equation 41.7 we have gt as a function of nu minus nu naught is equal to g star of nu minus nu naught. So you see that in case 1 we have gt is equal to g, and in the second case we have gt is equal to g star. So substituting the value of g star over there, we have sigma in is equal to the expression given in equation number 41.9, that is sigma in is equal to 2 pi square over 3 n epsilon naught ch into absolute square of mu into nu into g star of nu minus nu naught. So this is the case of a pure inhomogeneous broadening. Before that, over here in case number 1 we have discussed the case of a pure homogeneous broadening, and in the case number 2 we have discussed the case of a pure inhomogeneous broadening. So case 1 is the case of a pure homogeneous broadening, and case 2 is the case of a pure inhomogeneous broadening. We can remove the subscript in. You see that sigma in equation number 41.9 has a subscript in. We can remove that subscript and we can write sigma as such to stand for both types of absorption cross sections. That is, sigma can be written as 2 pi square over 3 n epsilon naught ch into absolute square of mu into nu into gt of nu minus nu naught. You see that here we have written the value of gt, because gt can take two values. For the case of homogeneous broadening, gt takes the value of g of nu minus nu naught, and for the case of a pure inhomogeneous case, we have gt is replaced by g star of nu minus nu naught. So this gt in equation number 41.10 41.10 can take two possible values. So this sigma can stand for homogeneous as well as for inhomogeneous case, depending upon the value of gt we choose, as discussed in case number 1 and case number 2. You know that as I, the intensity of the beam is equal to C into rho. Rho is the energy density divided by n, where rho is the density of the electromagnetic wave, and I is also given by F into h nu, where F is the flux of the beam and h nu is the energy of the photon in the beam. Thus we have, comparing the two values of I, we have capital F is equal to C into rho over n into h nu. and this is what we can introduce this value of f over here, that is W is equal to sigma f. So we have the sigma over here in equation number 41.10, and then we are putting the value of sigma and as well as the putting the value of f from equation 41.11. Then we can get the absorption rate W is equal to this 2 pi square over 3 n square epsilon naught h square into absolute square of mu into rho into gt of nu minus nu naught. So you see that here we have gt. That's why we have not written any subscript with W, because now this W given in equation number 12 can stand both for homogeneous case and for inhomogeneous case, because gt is present, and you know that gt can take two possible values as discussed in case number 1 and case number 2. For the case of pure homogeneous broadening we have gt is equal to g, and for the case of pure inhomogeneous case we have gt is equal to g star. So then this W can stand for two possible values for two absorption rates, that is for the absorption rate of the homogeneous case and for the inhomogeneous case, depending upon the choice of GT from cases 1 and cases 2, from case 1 and case 2 respectively. So for the case of single atom we have determined W1 2, that is the absorption rate, and W21 that is the stimulated rate. So W12 and SA stand for single atom. So we have W12 SA is equal to W21 SA. We can also regard W as the rate of stimulated emission for non-degenerate level, and sigma as the stimulated emission cross section. So you see that over this derivation is valid. We have derived this for the case of absorption transition and absorption cross section, but this analysis is equally valid for the transition, for the stimulated emission transition rate and for the stimulated emission cross section. So this is the end of slide number 41.